All objects, when dropped from a height, fall towards the earth. This happens due to the gravitational force exerted by the earth on the object. Suppose you drop simultaneously a small stone and a cotton ball of the same size from a height. Which of the two will reach the ground first? We see that the stone reaches the ground earlier than the cotton ball. So, we may falsely conclude that the heavier objects fall faster than the lighter ones. That is, the acceleration produced in heavier
Galileo
objects
showed
that
all
all
bodies,
in
whether
lighter
light
objects or heavy, fall at the same speed towards the earth. Galileo explained that the lighter bodies fall at a slower rate due to the resistance of the air. Robert Boyle proved this experimentally. He placed a coin and a feather in a long glass tube and evacuated it with the help of a vacuum pump. Robert Boyle observed that when the tube was inverted, both the coin and the feather reached the bottom of the tube at the same time. Thus, he concluded that the acceleration produced in all the freely falling bodies is the same and does not depend upon the mass of the falling body.
Projectile motion. Observe the athlete throwing a javelin. The javelin follows a curved path and lands on the surface of the earth. Such objects like javelin, which moves along a path determined by gravity and air resistance, are called projectiles. The path followed by a projectile is called trajectory. An object dropped from a height, an object thrown vertically upwards, and objects thrown obliquely upwards are examples of projectiles. In all these cases, the influence of air resistance is neglected. The velocity of the projectile varies from point to point. At each point, the velocity has components in the horizontal and vertical directions. The horizontal component of velocity remains unchanged throughout the flight. The vertical component of velocity continuously changes due to the force of gravity. Thus, the horizontal motion is a uniform motion, and the vertical motion is a uniformly accelerated motion. The magnitude of the vertical component is different at different points and is directed vertically downward. Let us now analyze the motion of a projectile thrown obliquely. Let a body be projected from a point O with initial velocity VO. The projectile makes an angle theta with the horizontal axis. The velocity of the projectile at any point of the trajectory goes on changing both in magnitude and in direction. The velocity can be resolved into two rectangular components, V0 cos theta along x-axis and V0 sin theta along y-axis. There is no acceleration in the horizontal direction. The vertical component of acceleration, AY, is equal to minus g. Substituting the value of AX and AY in equations 1 and 2 respectively, we get that is, the vertical component of velocity changes with time, and at the highest point, the Vy becomes 0. Let us now find out the resultant velocity of the projectile at any instant. The resultant velocity v is equal to vector Vx plus vector Vy. by parallelogram law of vectors. V is equal to square root of Vx squared plus Vy squared. V is equal to square root of V0 cos theta whole squared plus V0 sin theta minus gt whole squared. The direction of the projectile at any instant is given by the angle between the velocity vector and the horizontal. Tan theta is equal to Vy divided by Vx. From the equation Vy is equal to V0 sin theta minus gt, it is clear that Vy decreases when t increases and becomes 0 at p. At this point, the velocity is only along the horizontal direction. With further increase in time, the vertical component of velocity gradually increases in the downward direction till the particle strikes the ground. Horizontal range. The distance from the point of projection to the point where the projectile strikes the horizontal plane is called the horizontal range. It is denoted by the letter R. Time of flight. Time of flight of a projectile is the time taken by it from the instant when it is projected to the time when it strikes the point in a horizontal plane passing through the point of projection. T is equal to 2v0 sin theta by g. Range of projectile. Range of projectile is defined as the distance between the point of projection and the point where the trajectory cuts any plane. R is equal to V0 square sin 2 theta by g. Maximum height. Maximum height is the maximum value of the vertical distance attained by a projectile above the horizontal plane to the point of projection. In the figure, P is the point of maximum height. H is equal to V0 square sin square theta by 2g.
A lever is one of the simplest machines known. Basically, it consists of two forces, an effort force and resisting force acting around a pivot or a fulcrum. The distance from the effort force to the fulcrum is the force arm, and the distance from the resisting force to the fulcrum is the resistance arm. At equilibrium, the product of the force times the force arm is equal to the product of resistance times the resistance arm. It should be emphasized that the force and the resistance refer only to the rotary components of the actual forces. That's to say, the components that are directed at 90 degrees to the lever arm. The mechanical advantage the machine provides is determined by dividing the force arm distance by the resistance arm distance. That's to say, the mechanical advantage of a lever depends on where the forces are located. Regarding the uses of levers, there are three main uses of levers. First, change the direction of effort force, and this is what's going to be seen in first class levers. Second, increase the force, and that's what's going to be seen in second class levers. And third, as we are going to see in third class levers, there is gain of distance. Levers are of three classes: first class, second class, and third class, and each class serves a specific function. In first class levers, they have the pivot or the fulcrum located between the effort and resistance. Its mechanical advantage can be greater or less than 1. So here we can see that the mechanical advantage is more than 1, where the pivot is closely related or is at a short distance from the resistance. That's why the resistance arm is shorter than the effort arm. However, the mechanical advantage can be less than 1, as in this kind of lever, where the mechanical advantage is less than 1 because the resistance arm is longer than the effort arm or the force arm. The teeter-totter is a good example of this class of lever, and as we have said earlier, that first class lever, they change the direction of the effort force. As an anatomical example of this kind of lever, first class lever, is the action of the splenius muscle. The splenius muscle acting to extend the head across the atlanto-occipital joint. In fact, it's not only the splenius muscle, but the muscles at the back of the neck, while they act to balance the head across the atlanto-occipital joint, they act as on a first-class lever. In the second-class levers, the resistance is located between the effort and the fulcrum. An example of second-class lever is the wheelbarrow. Since the resistance arm is always less than the force arm, therefore, the mechanical advantage is always greater than 1. However, in this arrangement, the effort must always move a greater distance than the resistance. That's to say, the range of motion is sacrificed to gain force, and this is the main function of this kind of lever, that's to gain force. This type of levers is rare in the body, and the fact that muscle insertions are so frequently found close to the joints they move precludes many muscles from acting in a lever system of the second class. However, plantar flexion of the foot at the ankle joint is an example. Here, the pivot is at the metatarsophalangeal joints. The resistance is the line of gravity, while the force is the pull of the triceps suri muscle on the calcaneus. Again, I repeat that in this arrangement, the effort must always move a greater distance than the resistance. That's to say, the range of motion is sacrificed to gain force. And this is what we need here. Here we need to gain force in order to overcome the body weight. In the third class of levers, they have the effort located between the fulcrum and the resistance. A common example is found in a hammer pulling out a nail. Here, exerting a lot of force to pull the handle a little results in a larger movement of the nail. In this situation, the effort arm is always less than the resistance arm. To support resistance, effort must be of greater magnitude than the resistance. But the effort moves less distance than the resistance. Hence, in third-class levers, there is loss in effort but gain in distance. This class of levers is one of the most common in the body, since it permits muscles to produce distance of movement with minimal muscle shortening, although at sacrifice of force. A typical example is found in the biceps when the forearm is flexed. Again, I repeat that third-class levers are the most common levers in the body. This is supported by the fact that muscle insertions are so frequently found close to the joints they move. Therefore, the effort is located between the pivot and the resistance, creating a third-class lever.